All right, so yeah, it's equal to 300, then you get 1 minus 3x1 minus 2x2 equals to 0, right? And therefore you get 3x1 plus 2x2 equals to 1, right? All right, so let's again do the same thing. If x1 equals to 0, x2 is 0.5. So 0.2, 0.4, something like this, right? And of course, this line will still be parallel, so you already know what this will look like. It will look something like this. Right? Yeah?
So for this equal to 400, we get x1 is equal to 1. Why is that represented like?
Well, you can choose any point. I just chose this just for fun. If you're trying to plot a straight line, all you need is 2 points and you connect them, right?
But how is 0, 0, x1 is equal to 1?
Well, because if 3x1 plus x2 equals to 0, 0, 0, you can see lies on the line. No?
No, wouldn't it intersect that x1 is equal to 1? Why isn't it intersecting at x1 is equal to 1?
I mean, you can choose. I mean, that was the point I took. It is intersecting x1 equals to 1. It is going to intersect. If x1 equals to 1, x2 is minus 3 half. So that's why that point is off the board. But all you need is 2 points. You can choose any 2 points, right? Yeah. All right, and you can see every other line will be parallel. So now, if you look at f, what is happening to f if you're moving in this direction? F is decreasing, right? So based upon this, without even doing any calculations, can you tell me what do you think, where will f be a minimum? Sorry? Yeah, minimum, yeah, because we want to minimize f, right?
0, 1.
Yeah, where will it be minimum? Where it goes 0, 1/3. Because you can think about it, all you're trying to do is you're trying to march in a parallel line, right? Cost is high, keeps decreasing, keeps decreasing, keeps decreasing, keeps decreasing, keeps decreasing, keeps decreasing. Finally, you come up with this parallel line. You would like to go further, but you can't, because if you go further, you're outside the region of interest. So basically, idea is keep moving to this parallel line till the last point. And the last point will obviously always be one of the edges, right? So you can see the optimum solution will always lie along one of these points. Unless what? Can you give me an example where that will not necessarily be the case? No, we are only doing linear functions. But if the function is linear, can you give me a situation where the maximum or minimum will not necessarily lie around the vertices? Yeah?
When the line hits the other line and they're the same forever.
Very good. If f happens to be parallel to one of the constraints, right? In which case, there will be infinite solutions all along that line, right? Make sense? So for this problem, of course, the solution is x1 equals to 0, x2 equals to 1/3, and therefore x3, of course, is 2/3. Right? Now, just for fun, just to further convince ourselves that indeed is the correct answer, we can also calculate f at all 3 points. So at 0, 0, f is 400, we already know that. Let's calculate it at 1, 8, 1, 8. At 1, 8, 1, 8, f is it's going to be 400 minus 300 over 8 minus 200 over 8. So minus 500 over 8, right? So 8 was a 32, 2700 over 8. Right? What? Sorry?
White chalk.
Switch to white. Blue matches my jeans better, so if it rubs off, it's going to actually show. 2700. Well, let's just write it here. So f equals to 400 at 0, comma 0, right? It equals to 2700 divided by 8 at 1818. And finally, at 0, comma 1/3, it's going to be 400 minus 200 divided by 3, which is going to be 1000 divided by 3. Right? Right, 400 minus, no, what did I do? Yeah, x1 is 0, so it's minus 200 divided by 3, 1200, 1000, yeah. Okay, and so you can see clearly this is 400, this is 333, this is going to be, it's going to be 3 and 300 divided by 8. Well, about 340, right? Well, about 340, 400, and 333. So you can see, oh, no, yeah, so you can see that obviously a minimum solution is indeed this. Okay? So anytime you want to do linear programming, all you have to do is write down all your constraints, draw them on the graph, look for the region where all constraints are satisfied. You don't even have to draw actually f equals to constant lines. You can certainly draw that if you choose, or what can you do? Just look for values of f for all the extreme points and just figure out where is the minimum or maximum. It's really up to you which way you choose. Or you can draw some f's, see which way will be the first point they'll intersect, which will be the last point will intersect, and essentially just find out the values over there and you're all done. Okay? Easy enough, right? Now, of course, for 3 unknowns, this problem, of course, is fairly trivial. It's fairly easy to do. Now, in reality, though, the problem typically has hundreds and thousands of locations.
What if it's x, y, z?
What?
What if it's x, y, z?
So if you notice, in this case, it is x, y, z, right? There were 3 unknowns. We managed to eliminate. But yeah, if there were 3 unknowns, or really if there were
Or
20,
4.
30, 40 unknowns, yeah.
Okay, yeah, if there was 4, which makes it into 3D.
So then you cannot draw anymore, right? But nonetheless, the approach is still the same. How will you figure out constraints? Constraints are simply intersections, right? So basically, you take any two intersection, you'll find out the point of intersection, and essentially, if both constraints are planes. So right now, the intersection of constraints was what? A point, right? If you go to 3D, constraints will basically be planes, and the intersection of planes will give you a what? No, a line, right? So your region, of course, will be a polygon, right? A 3-dimensional polygon. If you go to higher dimensions, you'll basically have 4th dimension constraints. Intersections will give you a 3rd dimension planes, right? And so essentially, at the end of the day, mathematically, the problem is still very defined. All you have to figure out is where are the constraints intersecting, right? And then you locate all the intersection constraints, and from there you figure out what is the acceptable region. Or you actually don't even have to actually sketch traffic. All you have to figure out is the points at which the constraints are intersecting, and therefore you know that the optimum solution has to lie around the boundary. Now, saying it is, of course, is much easier than doing it. This is the kind of programming that, if you can actually figure out a good algorithm to do this, you'll become a billionaire, because there is no good algorithm to do this. The best way to do this is what's called simplex algorithm, and simplex algorithm does a good job, but in principle, you never know. Someday a better algorithm might come about. These kinds of problems arise in like a traveling salesman problem. If you have to, let's say, go to 100 different places, let's say newspaper delivery. If you deliver newspaper to 100 different places, minimize your total paths traveled. Where do you go first? Where do you go second? Where do you go third? And so on and so forth. And these types of problems, actually, newspaper problem is easy, of course, but these kinds of problems, like airlines have these kinds of problems, right? How do you basically decide where to fly from? Where do you go? Where do you have the hub? And all these. So these are essentially all optimization problems that are extremely common and extremely complex. And as I said, if somebody comes up with a better algorithm to solve it compared to the simplex, you could actually become a billionaire. Yeah.
So, from the time you got into, chemical engineering, I guess, research, whatever regime, how has like computer science and computer optimization affected the way you do research or affected, your job, I guess?
That's a good question, but I had no idea where that question came from.
Well, I mean, so many jobs have popped up nowadays where you're trying to do chemical engineering or nuclear engineering with
Right.
like coding. And so I'm just wondering what your experience is with that, because I feel like
I think in reality, life will never change in the sense that if you are well educated, you'll get great jobs and you'll be very successful because you'll be able to learn things very quickly. Go back to the same thing what I said earlier. Programming is not difficult. Chemical engineering is not difficult. Nothing is difficult. Once you know how to learn something, you can pick anything very quickly. All of you can, even if you have never touched a computer, all of you can learn programming extremely quickly. Right? So at the end of the day, it's not about what really the job is really advertising. In some sense, yeah, you need some background just so that you get interviewed. But I think a lot of companies are smart enough to know that their goal should be to hire the smartest student. And of course, in addition to that, the other aspect, right? There has to be very strong work ethic. A smarter student can never accomplish anything unless he or she has good work ethic, because you have to work, right? You cannot get anything done if you don't work. But hopefully the smart student is also smart enough to realize that he or she has to work, right? Otherwise he or she is not smart. So ergo, smartness is sufficient. Right? But anyway, so yeah, I think so the point I'm trying to make is that yes, computers are becoming more and more important. And it's good if you have a better understanding, better knowledge of writing computer code. But then the